Completely fair schedulers support symmetrical multiprocessing or SMP, in which any process, whether kernel or user, can execute on any processor. Yet, configurable scheduling domains can be used to group processors per load balancing or even segregation. If several processors share the same scheduling policy, then load balancing among them is not option. If a particular processor has a scheduling policy different from the other, then this processor would be segregated from the others with respect to scheduling. Configurable scheduling groups are another CFS features. As an example, consider the next web server that's running on my desktop machine. At startup, this server has a master process and 4 workers processes which act as HTTP request handlers. For any HTTP request, the particular workers that handles a request is irrelevant. It matters only that the request is handled in a timely manner. And so the 4 workers together provide a pool from which to draw a task handler as requests come in. It does seem fair to treat the 4 NICs workers as a group rather than an individuals for scheduling purposes, and the scheduling group can be used to do just that. The 4 NICs workers could be configured to have a single runtime among them rather than individual runtimes. Configuration is done in the traditional Linux way, through files. For runtime, sharing a file named CPU shares with the details given through familiar share commands would be created. Completely fair scheduler implementation. CFS requires efficient data structure to track task information and high performance code to generate the schedules. Let's begin with the central term in scheduling, the run queue. This is a data structure that represents a timeline per scheduled task. Despite the name, the run queue needs to be implemented in the traditional way, as a FIFO list. CFS breaks with tradition by using a time-ordered red block tree and a requeue. The data structure is well suited for the job because it is a self-balancing binary search tree, with efficient insert and remove operations that execute NO or log n time, where n is the number of nodes in a tree. Also, a tree is an excellent data structure of organizing entities into a hierarchy based on the particular property, in this case, of runtime. In CFS, the tree's internal nodes represent tasks to be scheduled, and the tree as a whole, like any run queue, represents a timeline for task execution. Red block trees are in wide use beyond scheduling. For example, Java uses this data structure to implement its tree map. Completely fair schedulers illustrates how the straightforward idea, give every task a fair share of processor resources, can be implemented in a low, cost by highly efficient way. It's worth repeating that CFS achieves fair and efficient scheduling without traditional artifacts such as peak time slices and explicit task priorities. The pursuit of even better scheduler goes on. Of course, for the moment, however, completely fair scheduler is a good and it gets for general purpose processor scheduling. That's all, and thank you for listening and watching my video.